Okay guys, this is the first note card in the 5th 6 weeks material, your last packet of the year. We're going to do a couple of note cards today, both related to slope fields. Slope fields, which are also called direction fields, though more commonly you'll hear slope fields, they are simply graphical representations of differential equations. If you remember on the last note card, note card of the 4th 6 weeks material, you solved separable differential equations. You actually found either a general solution, or if you had an initial condition where you could find C, then you found a particular solution. But slope fields are graphical representations of those solutions. They're basically a visualization of the parallel curves that solve the differential equation without algebra. In other words, we know that a derivative graphically is the slope of a tangent line. We're going to create a bunch of tangent line slopes that could formulate a pathway of this mysterious original solution. And why would we need slope fields? They are very helpful when you can't solve a differential equation. We learned in the last note card that many differential equations are not separable. Now we were practicing on ones that were separable, but ones that cannot be solved algebraically, you have other methods available to you, and one of those is slope fields. Another is something you wouldn't learn until BC calculus. But a slope field is a graphical representation of these differential equations, and they're very helpful when you do not have the ability to solve that differential equation with algebra. So let's talk about what we would do here. I'm going to raise this up a little bit now because we've talked about the whole top of the note card there. It says sketch the slope field for dy dx equals 2x using the table below. So this is my derivative. Okay. So I have a lot of points. If this was a free response, you'd be asked to fill in a little tangent line at each grid, at each point here. Now, you would never be asked to do this many on a free response. You would probably ask to maybe do 9 to 12. This is considerably more than that. However, I don't need this entire table. I am only going to use x values from -2 to +2, and just using the integers, no fractions. Now, why do I not need other points along the way here? I think you're going to see that in just a second. Let's go ahead and find the slope of the tangent line. Let's find the value of the derivative when x is -2. Notice I haven't put in anything for y here. And the reason is this particular differential equation does not have any y's in it. So it doesn't matter what y is. In other words, when x is -2, 2 times -2 is -4. dy dx is -4 regardless of what y is. So I'm going to go to x -2, and regardless of what y is, I'm going to try to sketch a slope of -4. So that clearly needs to be a negative tangent line, and that's fairly steep, so it needs to be steeper than the parent function. So maybe something like this. And you're given some latitude on this. So if your sketch is reasonably close, then you're going to get credit. Now, if it was positive, obviously that would be wrong. If you wrote a horizontal slope, that would be wrong. And if it wasn't steep enough, and you needed to compare it to another slope, you might get in trouble if the steepness levels weren't appropriate for the different numbers. But other than that, you get a little bit of leeway there. But that looks like a good first graphing there when x is -2. And notice it doesn't matter what y is, like we said. The slope when x is -2, dy dx is -4. We'll come back and talk more about that in a second. So now let's do -1. -1 times 2 is -2. So at every x value of -1, I need to sketch in a tangent line slope of -2. So here's the deal. Since I chose to make this steepness level as such, this needs to be flatter than this, because -2 is closer to 0 than -4. So you would get in trouble if you didn't noticeably show that this was flatter than your previous column. Other than that, we're pretty good. Okay, now let's go on. When x is 0, I get 0. Those need to be horizontal tangent lines. Okay? So horizontal tangent lines everywhere that x is 0. And now when x is 1, I'm going to get +2. That needs to be a positive tangent line slope. And once again, a little bit closer to the parent function steepness. And knowing that when x is 2, I'm going to be back to that 4 again. And that needs to be the steepest, doesn't it? There is a creation of a slope field. Now, it looks like my pathway pattern is something like this. It looks like the solution of this differential equation must somehow follow along this pattern. Let's actually solve this, because this is separable. we use this to teach slope fields, but this actually is a separable differential equation. So let's review what we did on the prior note card. I'm going to times both sides by dx, and I have separated. I have y's and dy's on one side, x's and dx's on the other. I'm going to integrate both sides. This is just a 1 dy, so the antiderivative of 1 with respect to y is y. And this would, the 2 is a constant multiple. This would be x squared over 2 when you bump up and divide, and the 2's are going to cancel out. And I get a plus c over here. So this looks like it makes sense because my solution is a parabola with some vertical shift that I don't know what c is. Maybe there's a 1, maybe c is 0, maybe c is -5. So whatever that y-intercept is, that would allow me then to know exactly where to put in the pathway of this guy. So hopefully you're seeing that a slope field is kind of like a road map or a blueprint on what the path of that solution equation would be. Now before we leave this note card, I want you to notice one other thing, because one thing you're going to be asked to do is pick a correct graphical representation of a slope field. Or maybe be given the slope field, pick the right differential equation from a multiple choice list. So one thing I want you to notice right now, whenever there are no y's in the differential equation, your slope field will be in what I call column format. In other words, the columns will all match up. And the reason the columns are all matching up is there are no y's in the differential equation. So only the x value determines the slope of the tangent line. So that slope is the same regardless of what y is. So if you see what I call column formatting, you should be choosing a differential equation that has no y's in it. Conversely, if you see row formatting, what do you think that would be? Hopefully somebody's saying a differential equation that had no x's in it and only y's. We'll look at some more little helpful hints as we go, but I wanted to make sure we were okay with that to begin with. Okay, so that is note card 69, slope fields, and now we're going to move to note card 70. And before we move to note card 70, I'm going to give a little bit of a reward here to the third period kids who are actually watching this right now. Okay? If you are watching this in class right now, like you're supposed to, in class, and you are on your phones, otherwise you couldn't be watching this, okay? I want you to write slope fields down. Write the word slope field on a piece of paper with the time that you wrote it and your name on it, and I want you to put it under the hole puncher before you leave this period. I'm going to grab those Thursday afternoon, and anybody who did that will be getting some bonus points on an assignment this week. Okay? So slope fields on a piece of paper with your name on it turned in under the hole puncher this period. Okay, note card 70, creating slope fields. To sketch a slope field, we're going to follow these 4 steps here. We're going to select any ordered pair and write a table, 3 columns, x, y, dy, dx. We're going to substitute those ordered pairs into the differential equation, and we're going to find the slopes. We're going to construct those short line segments. We've already done this. We're just kind of summarizing now. And for a particular solution, we're going to sketch in the curve using the initial condition and guided by the tangent lines. So let's take a look at an actual free response problem from a past AP test. Consider the differential equation dy dx equals x squared times quantity y minus 1. On the axis provided, sketch a slope field for the given differential equation at the 12 points indicated. So now I do need to include these points. When x is -1, I'm going to have 4 points for x -1. And those y values are 0, 1, 2, and 3. Same thing when x is 0. I'm going to have y's of 0, 1, 2, and 3. And when x is 1, I will have y's of 0, 1, 2, and 3 yet again. Now, we're just going to play a bunch of input-output games here. Okay? When I put in a -1 for x, I'm going to get +1 because we're squaring. And then 0 minus 1 is -1. I have 1 times -1. I have a dy dx value of -1. Now, at -1, 1. Well, can we agree that with all the x values of -1, this is going to be a 1? So really, it's just what's happening here that will determine the value. So let's put in a 1 for y. 1 minus 1 is 0. If dy dx is 0, what is that telling me about my slope field? We should have a horizontal tangent at that point, shouldn't we? In fact, why don't we go ahead and construct these as we go. So at x -1, y 0, I have a slope of -1. That needs to be a correlation there, and fairly flat, modeling the parent function. At negative 1, 1, I should have a horizontal tangent. Once again, we said that when x is negative 1, this x squared will always be 1. So I'm just looking at the y's right now. 2 minus 1 is 1. And let me go ahead and do this one. 3 minus 1 is 2. Okay, so let's graph just those before we move on. Let me raise this up a little bit here. Okay? And let's finish graphing just these before we move on. Okay? So when x is at x negative 1, y 2, I have a slope of positive 1. And at x negative 1, y 3, I have a slope of positive 2. That needs to be steeper than what you just did here. Right? Okay, now, this is going to be real easy. When x is 0, 0 squared is 0. 0 times anything is 0. So at every x value of 0, dy dx will be 0 regardless of what y is. So all the x values of 0 are going to get horizontal tangents. Now, look what's going to happen here. When x is 1, same as when x was negative 1. 1 squared is 1. So I'm just going to look at the y's to determine the values here. When I put in a 0, I still get negative 1, just like up here. When I put in a 1, I'm going to get 0. And I hope you're noticing that these four values are just going to repeat themselves, aren't they? So negative 1, 0, 1, and 2. So this column should be a mirror image of this column, shouldn't it? So let's put those in. At x1, y0, slope of negative 1. Horizontal tangent at 1, 1. Slope of positive 1 at 1, 2. And a little steeper, slope of positive 2 at 1, 3. And once again, that should match this column here. There is part A complete. Part B says, describe all points in the xy plane for which the slopes are positive. Okay, well, let's look for our positive slopes. Do I have any positive slopes when x is 0? Or I should say, I'm sorry, when y is 0. Do I have any positive slopes? Clearly not. Do I have any positive slopes when y is 1? No, they're all horizontal tangents, aren't they? All slopes of 0. I start having positive slopes when y is greater than 1 because I have them at 2 and I have them at 3. So I want to say that I have positive slopes for part B when y is greater than 1, but I need to make a stipulation of this because when x is 0, that's not true. When x is 0, I still have horizontal tangents. So I'm going to say that we have positive slopes when y is greater than 1, comma, however, when x is not equal to 0. Something like that would be sufficient for the AP reader. That's probably the most precise way you could write that. Okay, part C is going to bring in previous skills from the last note card. Find the particular solution y equals f of x to the given differential equation with the initial condition 0, f of 0 equals 3. Okay, I'm actually going to, rather than have to get up and go to the board, I'm going to turn and do this on the back so that we don't run out of room. So I'm going to recopy the differential equation on the back of your note card. If you have room, you can still work on the front, or you can move to the back with me whenever you need to. So I'm recopying this differential equation to do part C here. Okay? Okay, this is a review of the last note card from the last 6 weeks' materials. Separate, integrate. That is the phrase for solving separable differential equations. You want to separate and integrate. And I talked to you about how many points are awarded along the way here. This would be a terrible idea to leave this blank on a free response because you have 5 to 6 points at stake here. The first point comes from separating. So I'm going to multiply by dx while also dividing by y minus 1. So I'm combining algebraic steps there. Let's make sure you're okay with that. That was the result of timesing both sides by this denominator, but also dividing by this parentheses. You earned a point. I'm just going to kind of show you how this would work on an AP reader. You earned plus 1 right there. Now, let's get this ready for integration, okay? Well, I think we're ready for integration. I'm going to go ahead and integrate, and I have my dy, integrate dx. Now, you might be like, well, how is this ready for integration? Because the derivative of y minus 1 would be 1 dy. This is in do use setup, so we are automatically ready to go to the And clearly the right side is simply a nice little bump up and divide. X cubed over 3 plus c. Plus 1 for integrating the y's. Plus 1 for integrating the x's. Plus 1 for simply writing a plus c at the end of the x term. Look at that, 4 points. Now, point number 5 is going to come from using the initial condition. Just using it. Even if you messed up and got the wrong c number, if you use the initial condition to even try to find c, you're going to get a 5th point. So the initial condition was that when x is 0, y is 3. So I'm going to put in a 0 for x and a 3 for y. That is a plus 1 simply for using the initial condition, even if you mess up the c number. Now, if you messed up the c number, that would cause your final answer to be wrong, and that would cost you the very last point. Because that last point is going to come from solving for y. But you can't do that until you find that c number. So I had the natural log of 2. I don't need bars anymore because 2 is positive. And that's 0, so I have c is the natural log of 2. Okay, so now let's go up here and let's rewrite my particular solution. I'm sorry, my general solution. Let's rewrite this as a particular solution, with c being the natural log of 2. Okay, I need to get y by itself. We know that y is trapped in a natural log argument, and you get rid of logs with bases, and more specifically, I get rid of ln's with e's. So that will allow me to bring down the y minus 1, no longer in absolute value bars, because I no longer have a log argument. Now I want you to watch what's going to happen here. I'm going to take an extra step to do this, to make sure we're all okay with this. Right now, both of these terms are in the exponent position on the e, aren't they? But don't we, let me do a little sidebar here. Don't we have a law of exponents? Let me just make up something here. How about a to the x times a to the y? When you multiply like bases, you're allowed to add the exponents, aren't you? Well, the opposite is true then too. If I have exponents being added, I should be able to expand them back into this form. That's what I'm going to do here. So this will be e to the x cubed over 3 plus e raised to the natural log of 2. Because, I'm sorry, I messed that up there. Sorry, that should be multiplication. Multiplication, not plus. Thank you. Okay, because multiplying like bases, I would add the exponents, it would take me back to here, wouldn't it? Okay, and now e raised to the log in base e, that's going to cancel, that's just a 2 there, isn't it? So I have, this step would have been one I don't write, but I just want to make sure we're all okay with that. I would have gone ahead and gone to the next step here, where I bring this 2 in front and make that a coefficient on the e. So I have y minus 1 equals 2 times e raised to the x cubed over 3. Add 1 to both sides and we are done. And your last point would have come from solving for y. Y equals 2x raised to the x cubed over 3 plus 1. That is the particular solution with the initial condition stated that would go with this slope field. So now that I know initial condition, for example, when f of 0 is 3, so our initial condition, our solution, our particular solution goes through x0, y3. So I could now, if I had a bigger slope field, I could use this and I could actually follow the pathways and get an actual graphical representation of that solution curve. And that is note card 70. Okay, so let's talk about what I want you to do now for the rest of class, okay? Still have plenty of time left. This is a classwork activity, and this is to be turned in before the end of class. I need this particular paper turned in, 1 per student here, before the end of class today. This is a slope field card match game created by our awesome Nancy Stevenson. And this is your solution page. So what you have then is you have slope field cards, you have differential equation cards, and you have solution curve cards. So what you're going to do, and I'm going to have scissors left out for the substitute, you guys are going to go ahead in your groups and cut these up, okay? You can work in your groups, but each student should still be turning in their own paper, okay? Or I tell you what, actually you don't need to cut them up really. You just need to match, and then as you go you can scratch them off. So for example, slope field 1, you're going to say what differential equation should go with that. I'm going to try to see if I can figure out which differential equation should go with that, and then which conclusion card should go with it. So what you might do is get to the ones that are easily identifiable. For example, we said, hey, if you don't have any y's in your differential equation, like DE5 here, that means I should see column formatting on my slope field. Look at DE7. If I don't have any x's, I should see row formatting on my slope field. So use some of those little tricks we've learned and see if you can't start to match these up, and the more you go, there'll be less choices for the rest. You will be keeping all of the cards. What you will turn into me is this paper right here. Now I will say this before we go. I'm not going to give you the answer key. I want you to try to work it out. But conclusion card for slope field 7. There are actually 2 cards that could work for the conclusion of slope field 7. However, one of those cards needs to go to another conclusion. So if you initially find that, hey, there's 2 different ones that could work here, you're correct. But as you go through, you'll find that one of those needs to be used somewhere else. And that'll let you know which one to leave here, if that makes sense. So that is your classwork activity. And now let me show you what your homework is going to be that will be due next week. Right after this slope field card match game is slope field multiple choice. And this is several pages, however it's just 10 problems. It covers 4 pages though. 10 multiple choice problems related to slope fields. And that is the homework due next class.